What actually changes an object's motion? Let's understand force, friction and Newton's 3 laws in this quick Chapter 6 revision.
Welcome to Teaching Science. Have you ever wondered why a canoe moves forward when the person paddling is actually pushing the water backwards? Well, today we are going to understand this entire chapter step by step so that you don't just memorize it, you actually understand it. Okay, let's dive into our roadmap for today. We'll start with the concept of force, look at balanced and unbalanced forces, dive into Newton's first, second, and third laws of motion, and then wrap it all up with a final quick revision. Let's start with Section 1, the concept of force, pushes, pulls, and changes. You probably remember from your earlier classes that a force is, at its most basic, just a push or a pull. Let's visualize this. Think about a girl kicking a resting football. Before that kick, the ball is just sitting there, perfectly still. But the moment she applies a pushing force with her foot, boom, she changes its state from rest to motion and sends it flying in a specific direction. So we can definitely see that force can make stationary things move. But force isn't just about moving things around. Look at this. When you squeeze a lemon, your fingers are applying a force that literally changes the physical shape of the lemon itself. And we can actually measure this stuff too. If you pull the hook at the bottom of a spring balance, it stretches the spring inside. That stretch lets us precisely measure exactly how strong that pulling force is. So, let's nail down a formal definition. Force is what we call a physical quantity. This means to properly describe it, we need two very specific things. Its strength, which in science we call magnitude, and its direction. It is a vector. Think about it. If you just tell me, hey, I applied 10 units of force, I still need to know, did you push it forward, pull it backward, lift it up? Oh, and the standard SI unit for measuring all this force, that's the Newton, written with a capital N. Moving right along to Section 2, balanced and unbalanced forces, or, as I like to call it, the tug of war. Now, in real life, there's almost never just one single force acting on something at a time. It's usually a whole bunch of them. If you have multiple forces acting on an object and they perfectly cancel each other out, we call those balanced forces. The net force is exactly zero, meaning the object's state of motion is not going to change at all. However, if one force is stronger than the others, well, now the forces are unbalanced. This creates a non-zero net force, and that is exactly what causes an object to start moving, speed up, slow down, or completely change its direction. Think about it like this. When you try to push a heavy box across the floor, there are actually 4 invisible forces playing a game of tug of war. First, you've got gravitational force, or the weight, pulling the box straight down. But the floor is pushing right back up. We call this the normal force. Since the box isn't flying into the air or crashing through the floor, those vertical forces are perfectly balanced. Then there's your applied force, your push. But fighting against you is the force of friction from the floor. If the box is just sitting there stalled, it means your push and the friction are balanced. To finally make that box slide, you have to push harder and create an unbalanced force. And this builds directly into Section 3, Newton's first law of motion, also known as the law of inertia. Let's visualize this with Activity 6.1 straight from our NCERT textbook. Imagine stacking up a few Karm coins and flicking them with a rubber band across a wooden table. They stop pretty quickly, right? That's because rough wood has high friction. If you do the exact same thing on a smoother laminated table, the coins travel a lot further. And on a super polished marble floor where friction is incredibly low, they travel the furthest distance before stopping. So, as a thought experiment, if we could magically remove friction completely so it was exactly zero, that stack of coins would theoretically just keep moving forever. Which brings us perfectly to Newton's first law of motion. It states that an object at rest remains at rest, and an object in motion continues to move with a constant velocity unless a net force acts upon it. It's super crucial to understand this. Everyday objects don't naturally just want to stop moving. They only stop because an invisible, unbalanced net force, like friction, acts on them to slow them down. Next up is Section 4, Newton's second law of motion: mass, acceleration, and momentum. All right, so the first law tells us that forces cause changes, but Newton's second law gives us the actual mathematical rule for it. It tells us that when a net force acts on an object, it accelerates. The amount of that acceleration is directly proportional to the net force applied, but inversely proportional to the object's mass. This also introduces a super powerful concept called momentum, denoted by the small letter p. Momentum is simply an object's mass multiplied by its velocity. Think of a bullet fired from a gun. It has the tiny mass, but because its velocity is incredibly high, its momentum is absolutely massive. That's why stopping it requires such a huge force. Let's check your understanding with an NCERT example. Imagine we have a wooden block sitting on a table. If two forces, say 10 newtons and 6 newtons, both push the block to the right, what do you think will happen? They combine. The net force becomes 16 newtons to the right. But what if the 10 newton force pushes right and the 6 newton force pushes left? Now they're fighting each other. You simply subtract the smaller one from the larger one, meaning your net force becomes 4 newtons towards the right, since that's the direction of the stronger force. Now for Section 5, Newton's third law of motion, action and reaction. We've seen how forces act on a single object, but this final law explores how forces always interact in pairs. Newton's third law of motion states, whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. This is a total game changer. It means forces never, ever exist alone in isolation. They always occur in these equal, opposite action-reaction pairs. Now, what's really fascinating is how we can actually visually prove this in the lab. In Activity 6.6, we take two identical spring balances and hook them together. If you anchor one to a wall and pull the free end of the other one with your hand, guess what happens? Both spring balances will show the exact same reading. Even though they are pulling in entirely opposite directions, the force the first spring exerts on the second is exactly equal to the force the second exerts on the first. Pretty cool, right? Which brings us right back to the curiosity hook we started with. Why does a canoe move forward? Well, according to Newton's third law, when the girl uses her paddle to push the water backwards, that's our action force, the water exerts an equal and opposite reaction force, pushing the paddle, and therefore the whole canoe, right forward. So, we need to lock all of this amazing science into your brain. Let's jump into Section 6 for our final revision and recap. Here is your rapid 1-minute recap. Force is simply a push or pull that can change an object's motion or shape, and we always measure it in newtons. Balanced forces mean the net force is 0, so the object's motion does not change. Unbalanced forces, those cause acceleration. Newton's first law, the law of inertia, tells us objects maintain their state of motion unless a net force acts on them. The second law proves that acceleration depends on the net force applied and the object's mass. And the third law, forces always occur in equal opposite action-reaction pairs. Before you go, think about this. Next time you take a simple step forward, ask yourself, which of Newton's laws is actually pushing you ahead? That's all for today. Keep revising, and for more easy science explainers, subscribe to Teaching Science. If you found this explainer helpful, like it, and hit the bell icon for notifications about new explainers. See you in the next chapter.